Welcome one more time to Amy Smart Academy. So, I want to talk about something very important: thermal stress and what strain. So, I believe it's one of our videos that we talked about strength of materials, right? We say the material is said to be strong when it's actually exposed towards stress, a force, right? A force that is stress, right? When it's exposed to stress, you can know how strong the material is. Okay, so if I place a load on a material and the material is able to withstand that load, then I say that material is very strong. Okay, so we have thermal. Thermal means what? Heat, right? So thermal energy, so heat energy or thermal energy in most cases. So when we talk about thermal energy, we are talking about heat, right? Influence of heat on the body that causes what? Stress and what? Strain. Influence of heat on the body, so thermal stress. Thermal stress is the influence of heat on the body that's causing the body to deform or are causing distortion of the body, right? Deform or elongate. Deform, compress. Very good. So we talk about compression, right? When a load is applied on the body, it can cause deformation, and deformation we're talking about can cause compression, can cause tension, right? Tension as well. Can cause compression or tension. Let's put it that way. Compression and then tension. So it can cause compression of the body starts to squeeze. Remember I said compression is what? Push on the body. And tension is what? Pull on the body. Push on the body. That means if two forces are acting on the body and it's pushing it in, that means it's trying to squeeze that body. Okay. So we have tension, and tension is what? Pull on the body. That means if there is tension in the body, it's a kind of force that's trying to elongate the size of that particular body. Okay. Now look up. So we have thermal stress and what? Thermal strain. Thermal means what? Heat. Influence of heat that causes what? Stress and what? Strain. Stress. So stress, basically we say stress is what? Stress is equal to what? Force over area. So it's force by unit area. And then we say strain is elasticity, right? Or just say change in L all over L naught, right? Initial length. So change in length by unit what? Length. Okay. So that's basically what strain is. Rate of deformation of the body. So that's strain. Rate of deformation of the body. That rate of deformation could cause elongation. It could cause what? Distortion. That could cause compression. Sorry. Okay. So we have our young modulus. Young modulus is what? Stress over strain. Stress over what? Strain, right? And then stress, we say is what? Force by unit area. Then strain is what? Change in L over L naught. Okay, you put this together. I like putting it this way. Divided by what? Change in L over L naught. So we're going to look something like this. When you look at it like this, it's kind of easier to view that when you multiply, then you have L naught over what? Change in L. So it will look like this: F L naught all over what? E change in what? L. So this is basically how it's going to look like, right? So that is for your young modulus, right? You can see young modulus is equal to what? F L naught all over what? A changing what? L. Alright. So let's do something quickly. Let's do something. So this can also be written as E A change in L equal to F L naught. So let's remember something about linear expansivity, right? We say expansion is one of the influence of heat on the body. So it causes expansion of the body. So we say linear expansion basically is a change in length by unit length by degree rise in temperature. Change in length by unit length. Change in length by unit length by degree rise in temperature. So this is basically what it is. So if I make this guy simple formula, it's going to look something like this. Change in L equal to what? This L naught change in what? Sorry? Change in T, sorry. Change in what? T. Okay, that's in the temperature. Change in temperature. Okay. So if I include this here, I'm going to have E A, then instead of changing L, I'm going to have something like this. L naught changing T equal to F L naught. Okay. So I can remove this L naught from here. So if I remove L naught, so this will kill it, this will kill it. So my F now becomes young modulus times A. Remember what A is? A is area. Remember what alpha is? Alpha is what? Linear expansivity. Okay. So this is basically how to find common stress, right? But compressive force exerted on a body. Compressive force exerted on a body. Okay, let's look at. Alright, so look at this question. So we have a steel circular rod with a radius of 10 cm. So radius of 10 cm is placed between two vertical supports of 15 degrees Celsius. Two vertical means something like this. Vertical supports of at 15 degrees Celsius. That was the temperature. Okay. What compressive force is exerted by the vertical support if the temperature increases? So there is something here, and we say it's a circular rod. Don't mind this. Look like a circle, right? Circular rod. So it's a circular rod, and it is placed between two vertical supports, and then we said 10 cm radius, right? 10 cm radius. 10 cm radius. Okay. So what is the compressive force? If the temperature increases to 40 degrees Celsius. So change in temperature, remember, is equal to what? T2 minus T1. So we have 40 minus what? 40 minus 15. And what will that give us? 40 minus 15 should give us what? 40 minus 15 should give us these are 5, and these are 3 minus 1 is 2. Give us 25 degrees Celsius. Okay. And they give us a coefficient of linear expansion. Coefficient of linear expansion is right, alpha. They said is 12 times 10 to the power minus 6 degrees Celsius. Okay. So and then they give us young modulus as what? 200 times 10 to the power 9 Newton per meter squared. Okay. So we have this, the force of compression, or the compressive force, or the force as a result of a heat, right, acting on the body, or thermal stress. We said is Young modulus times what? Area times alpha times change in what? Temperature. Okay, the young modulus is what? 200 times 10 raised to the power what? 9. So times what we have again? We have area. So the area of that particular circular, remember circular. Area of the circle is what? Pi r squared. Pi r squared. So we have pi r equal 10. So it's in cm. That would be right. And this guy is in meters. So what do we do? Change it to what? Meters. Sorry for that. Change to meters. Change to meters. So how do I change cm to meters? 100 centimeter makes 1 meter, right? That means I'll divide this guy by 100. 10 divided by 100. So pi 10 over 100 all squared. So 10 over 100 will give you what? 0 points. So you have 1, 2, 0 0.1. So pi times what? 0.1 squared. So let's find out the value. Alright. So we got what? 0.0314, right? 0.031415. No, meters squared. Okay. So let's correct it. This would be times 0.0314 meters squared. Remember, this is in Newton. Let's clean this and put it as 200 times 10 to the power 9 Newton per meter squared. Okay, so times what again? Times what? So we have Young modulus, right, which is this. So we also have area, which is this. So the next thing is what? Coefficient of linear expansion, which is what? 12. 12 times 10 raised to the power minus 6, right? Times what again? Change in temperature. We have 25. Okay, so these are degrees Celsius and this per degree Celsius. Let's get into that. So this guy will cancel this guy out. And then this meter square will cancel this guy out here. And we're left with what? Newton. So basically, we've gotten an answer. That the answer must be in Newton. Okay, let's point that out. So we have 0.0314 times 200 times 10 raised to the power 9 times 12 times 12 times 10 raised to the power minus 6, right? Times 25. So I have 1.88 times 10 raised to the power 6. 1.88 times 10 raised to the power 1, 2, 3, 4, 5, 6. Raised to the power 6 Newton. That's about 1,844,000. 1,844,884,000, right? 884 times 10 raised to the power 6 Newton. So now that basically our answer on that. Let's solve it now. Let's solve it now. This is the right? So that means the force that would be the compressive force is started by the vertical support. This vertical support on this beam, right? Or this circular rod is going to be this at this temperature. If the temperature increase from 15 degrees Celsius towards 40 degrees Celsius. So there's an increase in temperature. So the amount of force needed to actually keep this guy And these guys, when he sat on this particular guy, will be what? Okay, let's look at another question. Alright, so let's handle this problem. So remember we said that the shear stress F is equal to Young modulus times what? A times linear expansivity, right? Times change in what? Temperature. Sorry. So we are given the aluminum bar is clamped to vertical. Clamped meaning 32 walls. Clamped means this we clamp, right? Something like this. It's clamped to vertical walls, right? So we're not to find at 30 degrees Celsius. Calculate the thermal stress on the metal bar. Calculate the thermal stress on the metal bar at 10 degrees Celsius. Okay, so what's stress? What's stress? Stress equals force all over area, isn't it? Force all over area. So in this case, you are not giving the area, so you're going to divide it by area, divide it by E. So this is basically what stress basically is stress. Stress is force over area. So we have this will kill this. So I'm going to have F over E, which is stress, is equal to that's Young modulus 70 times 10 raised to power minus 9 Newton per meter squared. Then we have this guy, that is coefficient of linear expansivity, right? Coefficient of expansion. So we have it as 25 and 10 raised to the power minus 6 per degree Celsius. And then we have temperature at what? We have 30 degrees Celsius. And then they said calculate thermal stress on the metal bar at 10 degrees Celsius. That means of a change in temperature, right? So change in temperature. So the change in temperature is going to be what? 10 minus 30. 10 minus 30 is minus 20. So that minus is not really important, so we have just 20. So let's point our calculator. What do we have? What will be the value now of stress? Right? We have 70 times 10 raised to the power minus 9 times 25 times 10 raised to the power minus 6. Then times 20. So we have 3.5 times 10 to the power minus 11. So Newton per meter squared. That would be basically because this degree Celsius, so this per degree Celsius and this degree Celsius. So we'll cancel out the result. What I'm left with was Newton per meter squared. Stress. Remember, stress equals force, which is in Newton all over area. It's in meter squared. Okay. So we have to calculate the tensile strain. Tensile strain. So tensile strain will be equal to what? Remember that this is Young modulus, right? And then we said that okay, let's do this. Young modulus was stress, right? All over what? Strain. So by cross multiplying, we're going to have what? E, Young modulus times strain equals stress, right? So if I divide it by E, I'm going to have strain or tensile strain will be equal to stress, right? Stress all over what? Young modulus. So my stress is what? 3.5 times 10 to the power minus 11 divided by the Young modulus was given as what? 70 times 10 to the power minus 9. So this is in Newton per meter square. This is also in Newton per meter square. Now take note, the strain always don't have a unit, right? Strain don't always have units. So that basically confirms it. So we have 3.5 times 10 to the power minus 11 divided by 70 times 10 to the power minus 9. We have 5 times 10 to the power minus 4. 5 times 10 to the power minus 4. So that will be our answer. That will be our answer. Alright, thank you very much. Thank you for being a part of this exciting moment. You can like, share, subscribe.